Welcome to day 17 of the 2024 Advent of Code. Today we have a problem where we're supposed to implement some opcode based language. I personally hate this type of problem, but hopefully they won't give us a chain of 14 of these like they did the other time with int code. That was torture. Let's see what they have here. So we have a 3-bit computer, which means that each item in our input is going to be a 3-bit number from 0 through 7. The computer supports 3 registers, which are basically variables, and the registers are not limited by any bounds. The computer has 8 instructions, which are each identified by a 3-bit number, which is an opcode, and each instruction uses the 3-bit number after as input, which is its operand. So basically each pair of numbers will be an instruction and an operand. A number called the instruction pointer, which basically refers to where in the program we are currently executing, tells us the position in the program. This starts at 0, and after each instruction it will increase by 2, except for jump instructions, which we'll get to in a bit. If the computer passes the end of the program, it halts. This is very similar to how computers work in real life. Ultimately, all high-level languages are interpreted by lower-level languages, and lower-level languages eventually compile into some form of bytecode, which basically works exactly this way. There is some opcode, which is just a number, operands, which are just numbers, and the computer just reads an instruction pointer at some location in memory and gradually shifts it jumping around, and eventually it receives instructions to halt. So for example, if we have the program 0123, then it will first run opcode 0 with an operand of 1, and then opcode 2 with an operand of 3. After that, we would exceed the end of the program, and so we would halt there. We're also given 2 types of operands, where each instruction will take one of the 2 types. A literal operand refers to just the value itself, so literal operand 7 is the same as just the number 7. And then there are also combo operands. Combo operands 0 through 3 are literals, 4 through 6 represent the 3 registers, and 7 is reserved and will not appear in any programs. So let's go through the 8 instructions quickly. ADV, which I think stands for A divide, is opcode 0 and performs division. It divides the numerator, which is the A register, by the denominator, which is the combo operand as the exponent on top of 2. So for example, if we have 0, 3 as our program, then that will take the A register, divide it by 8, which is 2 to the power of 3, and then it will truncate that value to an integer and write it to the A register. Note that dividing by, this stands for integer division here, dividing by 2 to the power of some value x is the same thing as doing a right shift x. A right shift basically takes the bits and shifts them to the right. So here's a good time to introduce binary because that will heavily be required for this problem. Our usual way of writing numbers is what's known as base 10. For example, if I write the number 271, what this means is it's 2 times the place value, which is 100, plus 7 times the place value, which is 10, plus 1 times the place value, which is 1. So this is where we get 271 written like so. It's 2 of 100 plus 7 of 1, or 7 of 10, and then plus 1. This is known as base 10 because each time we go left, the place value is worth 10 times as much as the previous one. In binary, we instead increase our value 2-fold each time, and our only digits available are 1 and 0. This is how computers store data because it's easy to represent in switches. The switch is either on or it's off, representing a value of 1 or 0. So for example, the number 5 is 101 in base 2. Let's see what that means. This is 1 times its place value, which equals 1. This is 0 times its place value of 2, which equals 0. And this is 1 times its place value of 4. And so if we add these all together, we get our recognizable value of 5. What right shifting means is it takes all of these digits and it moves them to the right, and any digits that get cut off beyond the last digit just get removed. So it is exactly the same as dividing by the nth power of 2 and removing all of the decimals. So when we do a divide 2 to the power of x and cut off the decimals, we are just taking a and shifting its bits to the right by x. This may make a bit more intuitive sense if we imagine dividing a by 10 to the power of x. Let's say x equals 3 here. Then if we divide a by 1000, we know that we just get the digits of a, and we shift the digits over to the right by 3, or equivalently the decimal point to the left by 3. And then if we cut off all of the decimals, we've basically just taken the last 3 digits of a and removed them. For example, if we have 27156 and we divide that by 1000, we got 27.156. And if we cut off the part after the decimal point, we just get 27. So it's the same logic as in base 10, where dividing by power of 10 cuts off those digits. In base 2, dividing by a power of 2, in this case 8 for example, also just cuts off the last couple of digits. So rather than division, this makes more sense to think about as right shifting, but for now we can think of it as both. The second instruction with opcode 1 which is called BXL or BXOR literal, takes the bitwise XOR of register B and the literal operand. So remember that this means it's just the operand's numeric value. This links us to a Wikipedia page on bitwise XOR. As we've already explained binary, this is fairly easy to understand. The XOR of two values is the exclusive OR, meaning it's true if either but not both of the previous values were true. So for example, we denote XOR with a caret in computing usually. Also common is a plus in a circle. This is more common in Boolean logic settings, and the caret is more common when you're actually coding. So 0 XOR 0, that would be 0 because 0 or 0 is not true. 0 XOR 1 is true, 1 XOR 0 is true. But 1 XOR 1 is not true because it's not exclusive OR, because both of these values are the case, and so exclusive OR forbids them both from being on at the same time. So that's what the Boolean logic exclusive OR means. And now for bitwise XOR, we basically just take the bits and line them up. So let's say A is equal to 7 and B is equal to 5. If we want to take the bitwise XOR of that, we're first going to convert them into binary. And then we line up their digits along the right, and then we just look at each column and take the XOR individually. So we see here that the XOR of 7 and 5 is 3. And if we take a bit more of a complex example, if we have A is 13 and B is 6, then A is equal to 1101 base 2, and B is equal to 110 base 2. So if we line up the digits on the right, we get 1011, which is 11 in base 10. So that's how bitwise XOR works. The third instruction, BST, takes the combo operand and takes it modulo 8. So modulos is the remainder when dividing. There's another Wikipedia page linked here, but basically it just takes the lowest 3 bits. A bit is also a common name for a single digit in binary. So when we take modulo 8, we are basically doing the opposite, where instead of cutting off the right few digits, we cut off the left few digits. So for example, 11 mod 8 is equal to 3, because if we write 11 as binary, it's just taking everything but the last 3 digits and removing them, or just taking the last 3 digits. And this value is written to the B register. JNZ is jump if not 0. This is a common instruction that's a real thing that is used in most machine code. Opcode 3, it does nothing if the A register is 0, but if A is not 0, it jumps to the literal operand. So for example, if we have 3, 0, that means that if a is 0, nothing happens, and if a is not 0, it goes back to instruction pointer 0. And if the instruction pointer jumps, then the instruction pointer does not get increased by 2 after the instruction. BXC is B XOR C. Opcode 4 takes the bitwise XOR of register B and C and then stores the result in B. This one takes an operand but doesn't actually use it. Reason for this is basically just to avoid being annoying, because if it didn't take an operand, then we'd need to shift the instruction pointer by a different amount between steps. We don't want to do that. The out instruction, opcode 5, takes the combo operand value modulo 8 and then outputs that, and we get all of our values outputted separated by commas. BDV is the B division operator. With opcode 6, it's basically the same as ADV. Remember that ADV took the A register and divided and right shifted it by the combo operand. BDV instead takes the A register and right shifts it by the operand and then stores it in the B register. It is clarified here that BDV still takes the numerator from the A register and not the B register. And finally, CDV is basically the same thing. It takes the C register and it stores into the C register again, but again, it still uses the A register as the numerator. We're given some examples here, and our first task is to determine what the program is currently trying to output. So we're given the registers in 3 lines and then the program on the last line. So let's first grab our input. Again, this is a day where using regular expressions to grab the input is going to be easier. We can just grab the initial values of the A, B, and C registers, as well as the program, which will be all of the remaining items. This star here basically means when we unpack the right-hand side, A, B, and C are the first 3, and program just picks up the remainder. So we're going to use a regular expression to find all blocks of digits from the entire input file, and then we're going to map all of those to integers. So if we see what we have read for input, you can see that A, B, and C are read successfully, and then program is a list containing the remaining values. Same thing goes for the actual input. So now let's simulate all of this. So we're going to maintain a pointer which starts at 0, and we're going to maintain an output array which starts out empty. So long as the pointer is within the bounds of the program, we will get the instruction from the value at the pointer, and we will get the operand as the next value. Let's also make a function to get the combo operand. If the operand is between 0 and 3, we return its value directly as a literal. If it's equal to 4, we return A. If it's equal to 5, we return B. If it's 6, we return C. And otherwise, we can throw an error. Just in case we run into any issues. So now we can look at all of the possible instructions. So for opcode 0, we do our division thing. So if instruction equals 0, which is the ADV operand, we take the A register and we right shift it by however much the combo operand is. So this gets the combo operand, and then we divide it by 2 to the power of the combo operand, which again, remember this is the same as right shifting. If the instruction is 1, which is BXL, then we do B equals BX or the literal operand, which is just the value itself. In Python and most other languages that I know of, the caret is used to denote bitwise XOR. If the instruction equals 2, which is BST, we take the combo operand, modulo it by 8, and store it in the value of the B register. If our opcode is 3, we have JNZ, which is the jump if not 0. So if A is not equal to 0, then we will set the pointer back to the literal operand, and then we will not skip forward by 2. So after this if-else chain, we're going to do pointer plus equals 2 to advance to the next position. So here we can just continue to skip over that, or we could also do something like pointer equals operand minus 2 so that this jump brings it back into place. I prefer continue because it's cleaner than relying on the operations canceling out. If a is equal to 0, then nothing happens, and so we would proceed to the next instruction as usual. If the instruction is 4, which is BXC, we get the XOR of the B register and the C register, which is stored to B. Notice that this condition does not use the operand at all. If the instruction is equal to 5, that's our out instruction. So we're going to print out that value. We'll print them all at the end, which makes it easier to separate by commas. So we'll just add it to the output array. And this gives us the combo operand modulo 8. If the instruction is equal to 6, that's BDV. So B equals a right shift combo operand this time. And if the instruction is 7, we do CDV, which is C equals a right shift combo operand. At the end, we output the output comma separated, which gives us our answer for part 1. So part 1 is not very interesting. It's just tedious. It's basically just copy pasting the simple sub steps one by one and hoping you don't make a typo, because if you make a typo, these problems are also really, really annoying to debug. I don't like these types of problems, only for part 1. Part 2, on the other hand, I really enjoy this problem. I am a fan of these types of reverse engineering problems, so given how fun I found part 2, I'd say part 1 was worth the slight annoyance. The problem comes in trying to make a video for y'all, because the way that you solve part 2 is you kind of just manually inspect the program and reverse engineer it. Now, I don't mind doing that. I find that fun, but it makes it hard to write code that I can just put on my GitHub and say, if you run this on your input, you'll get an answer, when the intended way to solve this is to manually inspect the code and do custom things. So I will show 2 things. Firstly, I'll show how I solved this, so if you want to know how to do these sorts of problems, you can look through that, and then I will work through writing out actual code. The second part won't really be necessary if you just want to learn how to do these types of problems, but I feel like it'll still be educational and probably fun, if not mildly annoying. Anyway, we are supposed to output another copy of the program with this program. So that's known as a quine, Quine. I'm not actually sure how to pronounce that, but it basically refers to a class of programs that output themselves. The value in register A seems to have been corrupted, so we're going to need to find a new value to initialize register A to, so that the program's output instructions produce a copy of the program itself. So for example, given the program 035430, the initialized value in register A must be 117440 in order to get this output. We want to know what the lowest positive initial value for register A that causes the program to output itself is. So as you can see from my output, checking every possible value and running it against the simulator is not even slightly possible. The way we do this is instead by just looking at the actual code and reverse engineering. So let's take a look at our test program. So this time it's changed. We have 035430. So recall that 0 is the ADV instruction, so A equals a right shift by the combo value. 3 is from within 0 to 3, so its combo operand is just the same as itself. And then we do 5-4, which outputs the combo operand. 4 refers to register A, so it's A modulo 8. And then we do opcode 3, which is JNZ, so we get if A is not 0, then we jump back to 0, which goes to the start of the program. So basically what this is doing is starting from A, we right shift it by 3, so divided by 8, output it modulo 8, so the lowest 3 bits, And then if it's 0, if it's not 0, we go back to the start. So we keep repeating this until we hit 0. It's effectively the same as doing do a equals a right shift 3 output a mod 8 while a. Or equivalently, if we shift things around a bit, it's something like while a output a mod 8, and then a is a right shift 3, or something along those lines. Something similar to this, basically. So if we run through this with the provided answer of 117440, we can see that this lines up with our expectations. A equals a right shift 3. So at this point, a is now 14680. And then we output a mod 8, which is equal to 0. And then a is clearly not 0 right now, so we jump back to the start, which would start this all over again. And then a mod 8 is 3. So you can see that this is starting to print out the program. So basically what this is doing is it's just dumping each block of 3 bits. And we can see that if we convert 117440 to a binary number, each block of 3 gives us the next thing we need to output. So basically we drop the last 3 bits, and then we output the next 3 bits, and then we drop those 3 bits, output the next one, so we get 0, 3, 5, 4, 3, because there's basically infinite zeros to the left. And then as the last step, because a was equal to 3 here, we still jump back to the start, so we drop those bits, output the next 3 bits, which are 0, and then we terminate the program because a is now 0. So that's how we get our output of 035430. Of course, our program is going to be significantly more complicated than that. So let's quickly go over what this is. And by quickly, I mean not at all quickly, because this is going to be a bit tedious. So we have BST, which takes the combo operand modulo 8 and stores it into B. 4 refers to 8, register A, so we get B equals A modulo 8. Note that this logic will be different for your program, so basically you'll have to go through your program and decode it yourself. If you happen to have the same input as me, then you're lucky here, but if you don't, you'll have to go through this step yourself. Then we have opcode 1 with operand 2, which is the BXL. So B equals B XOR the literal value of 2. Then we have opcode 7 with operand 5, which is the C divide operator. So that's C equals A divided by, or right shift by the combo operator, and 5 refers to B. Then we have 4-1, which is opcode BXC. So that's the bitwise XOR of B and C. So B equals B XOR C. Then we have 1-3, which is BXL again. So B is B XOR a literal value of 3. Then we have 5-5, which outputs the value of B modulo 8. Then we have 0-3, which is the A divide operator. And then we have 3-0, which is the J and Z operator. If A is not 0, we go back to the start. So that's what I have for my code. Basically, at the start of each iteration, we set B equal to A modulo 8. Then we flip its second bit. We take it XOR 2. We take C equals A right shifted by B, XOR B with C, XOR B with 3, and then output the lowest 3 bits of B. And then we go to the next block of A. So the way we're going to do this is we're basically going to work backwards and reverse engineer a value of A that works. So I'll do a couple of steps manually, and then we'll move to doing this programmatically because it will be easier that way. So working backwards, the last value we need to output is 0. At this point, A needs to be less than or equal to 7. If A is equal to 8 when we enter this loop, then A will become 1 or greater when we exit this loop, which means that we'll loop again, which means that we will output again, which is wrong because this needs to be the last output. So at this step, going into this, A needs to be somewhere between 0 and 7. So let's just try things, because reverse engineering this step fully is going to be a bit difficult, but we can just try all possible values of A running forward because there are only 8 of them. So if we try A equals 0, then B equals 0, caret 2, B equals 0, B equals 2, C equals A right shift B, which is 0 right shift 2, so C is 0. B is currently 2, and 2 XOR 0 is still 2. 2 XOR 3 is 1, which means that B is 1, so we would output 1. So that's not correct. What if A is equal to 1? Then B is 1, B XOR 2 is 3, so now B is 3. C is a right shift 3, which is still 0, because 1 is too small, so 1 right shift 3, all of the bits would get deleted. So C is 0, B is 3, B XOR C is still going to be 3, and then B equals B XOR 3, which means that B is now 0, meaning that we output 0. So that works. Proceeding next, what this is basically telling us is that when we get to the next loop, A must be equal to 1, which tells us that when we right shift A by 3, we need to get 1. So we can reverse this step by left shifting 1 by 3, which is going to be the same thing as multiplying by a power of 2. So that means that we need A to be larger than 8 and smaller than 16 at this point. Because if we do something larger than 8, the remaining bits less than 8 are still going to be truncated. But if we do 16 right shift 3, then we'll get 2. So it has to be 8 with some number of bits tacked on. You can think about it this way. We need to get to 1 in our next loop, which means that we can have any 3 digits here because when we right shift 3, they'll get deleted. But in order to do 16, this will need to be a 2, which would be wrong. So we can have any 3 bits here, which correlates to a value of between 0 to 7. So again, we can just search through all possible values because there are only 8 of them. So what we're basically trying at this step is A is now equal to 8 plus some value between 0 and 7. In fact, that value, because A modulo 8 is the last 3 digits, is just the new value of B that we're testing. So if we try 0, B equals 0, B now equals 2, C equals A right shift 2. In this case, since A now equals 8, 8 right shift 2 is equal to 2. So C is equal to 2, B is equal to 2, so now B is equal to 0, now B is equal to 3, so we output 3, which is correct. So B equals 0 would work. And we can go so on and so forth. We can test this out. So we saw that our analysis said that if we feed A a value of 0, we should get an output of 1, which is true. If we feed A a value of 1, we should get 0, which is true. And if we feed A a value of 8, we should get 3, 0, which is also true. So this reverse engineering is working out so far, and we can continue the process programmatically. So I'm going to hard code what I have first, and then try to code a more general solution that should hopefully work for all inputs, although it's hard to verify that without seeing all of the possible inputs. So we're still going to use regular expressions to grab the last line. We're going to do re.findAll on all digits. We're going to ignore the first 3 because I believe register B and C will always be initialized to 0 because it makes the searching a bit complicated if it's not. And then we will map these all to integers. Convert to a list and assign that to a program. So that's the program that we need to output. And now what we're going to do is we're going to do this recursively. And the reason we're doing this recursively instead of iteratively looping backwards is because of a slight complication here. Notice that there is a step here where C equals A right shift B. In all other lines, we only depend on the value of A mod 8, which means that we only need to exhaustively search those 8 possibilities. However, C depends on the entire value of A, including parts that will mostly be relevant in the next steps, which means that we might end up in a situation where actually no possible value here works because of this. If that is the case, then we need to go back to our previous step and try to find a new value that goes here that will work. Because we are going for the lowest value of A possible, so we'll stop when we find the first value that works, but that might break the subsequent steps, or since we're working backwards, the previous outputs. And so if one of our answer values breaks something further down the line and makes it unsolvable because of this line, then we need to go back and try again. So let's make a function that will find the answer given the program and the answer up to that point, which is initially 0. The answer up to that point is basically the value that needs to be output when we do our closing A equals A right shift 3 step. So we're going to exhaustively look through our options. So for T, which I'll identify, or rather for B in range 8, since B is just equal to A mod 8, then A is equal to answer left shift 3 plus B. We can also use bitwise OR here. Bitwise OR is a pretty logical operator. It's basically just takes our digits pairwise and it just takes the OR value of them. So unlike XOR, 1 or 1 is equal to 1. And so we just do a column-wise OR of all of our bits. It doesn't really matter what we do here. I think OR should be like 1 clock cycle faster maybe. I'm not even sure if that's true. In any case, it doesn't matter in Python. So now we can go through all of these steps. So this step is already done for us because we're doing that in our loop. B equals B mod XOR 2. One important thing to note is that if you modify B within a for loop, it's fine because when it iterates to the next value, it will reset B. This doesn't work in languages where you have the 3-part loops like for B equals 0, B is less than 8, B plus plus, because then if you modify B, it will exit in the next step because B is not reset here, it's just modified. But if you're looping through a range, then this works fine. C equals A right shift B, B equals B caret C, B equals B XOR C, or 3, and then we print out B mod 8. So to determine if this is the correct value, we need B mod 8 to be equal to the first value the last value in the program because we're looking backwards. If this is the case, then this is a value that will work up to this point. We can't guarantee this is the final answer because we might run into problems further down the line. So what we're going to do is we're going to look for the sub answer. So the sub answer is equal to find, where we take all but the last value of the program, and the answer up to this point is equal to answer left shift 3 plus B, or equivalently just A. Again, this is basically the value that we need to have when we do this step. And this is relevant because of this step. So if we found no solution here, we can skip over this. Otherwise, we just return the sub-solution. So basically, when we recurse all the way to the bottom, if we find our answer, we can return it. And our terminating case for our recursion is if the program is empty, then we just return the answer up to this point. And so we find the program with an initial A value of 0. I wonder if this is because these names are getting shadowed. No, that wasn't the issue. I do wonder if the issue is because I'm assuming that this works. Okay, so I took a moment to debug. I completely forgot. It actually does matter if you put a plus sign or here because of operator precedence. Yeah, I entirely forgot about that. If you're going to use a plus, you would have to put this in brackets. So anyway, that's slightly awkward. That aside, this gives me my answer for part 2. So you can solve this problem using roughly similar tactics, where basically you reverse engineer your code, look for the way the processing iterates through each stage, and then set it up to reverse engineer and search through the possible search space. The reason this works so quickly is because instead of just looping through every single A value naively, we break it down into individual stages, so the amount of time it takes is roughly equal to the length of the program instead of exponential to that. And we can basically early on call out answers that won't work. We don't necessarily just have linear time because we do need to backtrack every now and then, but overall it is still very fast. So now, for the sake of interest, I'm going to attempt to write a solution that should work for basically all inputs. Now, the way we're going to do this is basically this part here, this middle block is the interchangeable part. You can basically analyze your code, and assuming it ends with the same setup, you can basically just swap out this block of 5 lines for the way that your program does these steps. So let's go over this together. Okay, I needed to do a bit of a cut here because I made some assumptions, and after I finished recording, a member of my Discord server gave me an input that actually went against my assumptions. So let's try this again. So let me just quickly bring back what we had previously. We have list map int of the all but the first 3 digits, digit blocks. There's a better way of doing this input parsing, but I don't care. So we're going to make 3 assumptions that are different from the 3 I initially had. These should hopefully be correct. Firstly, the last instruction is going to be a jump not 0 to 0.0, because if it isn't this, then we have a setup stage before the loop, and that gets a bit complicated and confusing. So we're going to assume that it's a JNZ 0. Another thing is that we will have an output thing. We'll have exactly 1 output per loop. And finally, we will have exactly 1 operation that modifies the value of the A register, which is A right shift 3. If A gets modified in any other way, then this reverse engineering becomes significantly more complicated, and generally Eric is not going to give people different inputs that have vastly different complexities, so most likely this is not going to be a concern. So those are the 3 assumptions. The output step is probably going to be after everything that modifies B or C, but just in case it isn't, we won't assume this. So we're going to assume that the last 2 instructions are 3-0, the jump not 0 to 0. And then we're going to implement our recursive find algorithm from before. The reason we are now using input is because we're going to be we're basically, instead of using that block of 5 lines I had earlier, we're just going to read the program and execute it directly. So let's see. We're going to test the value in range 8. A is going to be the answer left shift 3 or T. And then we're going to set up our program here. So we're going to initialize our output to none. Again, remember that we're making the assumption that the output only has that the loop only has 1 output per step. Otherwise things get, again, more complicated in a way that likely wouldn't be fair to different competitors. If these assumptions don't work for your input, please do let me know in the comments so I can hopefully look into fixing that in a recap stream if I do one for this year. So output equals none here, and then we're going to go through the program. So for pointer in range, from 0 to the length of the program up to 2. Again, we're making the assumption that we're not going to have any jump instructions outside of the end, because if there are jump instructions in the middle, then the reverse engineering also gets drastically more complicated. So we're going to skip the last set of instructions, and we're going to do this. So instruction equals the value in the program at that pointer, and the operand is the next. We also need to initialize the B registers and C registers. We're going to assume that they're always 0, because if they start out as non-zero, then this also complicates the search in a way that would be unfair to people. We also need our combo function. If operand is less than or is between 0 and 3, we're going to return the operand. If it's 4, we're going to return A. If it's 5, we return B. If it's 6, we return C. And otherwise, we throw a yeah, we're going to raise a runtime error. Okay, now getting onto the implementation of the loop part, which is the interesting bit. If the instruction is equal to 0, which is the A division, then we're going to assert that the operand is equal to 3. The reason for this is because this entire thing relies on A basically being a bunch of octets, which are like 3 bits, that we go through one by one, and basically each loop just pops off the next octet and checks its value. So if we're going to be modifying A in any way other than right shifting by 3, this assumption falls apart, and so we would need to get an error for that. Also, I should make the error messages a bit more productive. Program does not end with JNZ 0. And here we get program has ADV with operand other than 3. We're going to ignore this instruction because we don't actually need to perform this instruction. We just need to know that it happens exactly once for the purposes of the entire structure of our find function. We also do need to assert that this instruction actually happens. So we're going to say ADV3 or ADV3 equals false. If this happens, we're going to say ADV equals true. ADV3 equals true. We also need to make sure this doesn't happen more than once. So if ADV3 is true, we're going to, or rather we can assert ADV3 is false. If it's not false, we're going to say program has multiple ADVs. So that's another thing that can't happen. If the instruction is equal to 1, then that is the BXL instruction. So we can do that. B is B XOR operand. If instruction equals 2, that is the BST operand operation. So B equals combo operand modulo 8. If instruction is 3, then we are going to raise an assertion error. Program has JNZ inside expected loop body, because if we have jump operations inside of this segment, then that becomes a lot more difficult. I think assertion error probably makes more sense here. If the instruction equals 4, that's BXC, so B equals B XOR C. If instruction equals 5, that's our output. So here we will collect our output. We're going to assert that the output is currently none, because if it isn't none, that means that we have multiple outputs. So we will raise an assertion error of program has multiple out, which is an issue because that would complicate things. Otherwise, we will set output to combo of the operand. If the instruction is 6, that's B divide. So like that. And if the instruction is 7, we get C divide. Again, like before, we're going to check if the output, which we collected from the output step here, which could be anywhere in the program and could output either B or C, or theoretically A, but I think that would also be disadvantageously complex. Doesn't really matter. We're not checking for that here. If output is equal to the last item in the input, then that means, or rather output modulo 8, then that means that we have found a possible answer. Again, this might not be the only, or this might not work, so we're going to need to recurse to the next step. We're going to check for all but the last expected target. I should probably name this target instead of input. And the answer going into this step is going to be the value of A at this position, just like before. If sub is none, continue. Otherwise, return sub. And so at the end, we just print out target, program with an initial answer value of 0. And I forgot to add the break step as well. If target is an empty list, then we just return the answer. And that gives me my answer for part B. And if we test it with another input, this is the input that was sent to me by a member of my server. You can see here that the output step, that the A divide step occurs in the middle, which broke one of my initial assumptions, and then we output B at the end. So this is also a possible case. We can see that our program should be able to handle this perfectly fine and obtain this as the answer. And just to make sure this works, we can always just try plugging this back in, pulling the part 1 solution and running it to see if this works, and we see we get 2417750344175530. So we can see that this has worked for at least 2 inputs. So hopefully I have not made any assumptions here that are incorrect. However, if you do find that your input does not satisfy my assumptions and gives an error, please do let me know in the comments so I can cover a fix in a future video or VCAP stream. In any case, thank you for watching. I hope you learned something from this video, and I'll see you again next time.